ANOVA is probably a general term, analysis of variance. I guess your book, this problem is referred to as ANOVA, but everything that we're doing is sort of some form of ANOVA, if you want. But it doesn't matter what you call it. It's just good to know. So this is a special case. If you want to call it ANOVA, if you want to call it something else, this is a hypothesis testing problem where you want to test whether in a linear model, whether the part that is besides the intercept, so everything else besides the intercept, does it have any effect? So are any of the covariates informative or useful for predicting y? And so let's see. What we can do is set all the coefficients to 0, right? All the coefficients of x to 0, and then what we get is an intercept only model. And so this would be our reduced or simple model. And then we have reduced model or simple model. That would be M naught. And then we have a full model, which is the full model with p covariates. And you're testing the full model against the reduced model and a reduced model against the full model. And you can use a t-test, an Ftest. So how do we do an Ftest here? Anyone remembers maybe? You guys wake up maybe a little bit. Anyone remembers how to do an Ftest here? Yes.
Yeah, the residual, it's the same as the last time you find the residual minus the SSE divided by minus residual of the full one divided by a series of freedom divided by the full model series freedom, that's it.
Right. How do we get the SSE of the reduced model?
We set all the betas equal to 0, so we basically only have whatever we get only one parameter.
Yeah, so we have this.
And then you get that value to be able to do it. You can either do it from there, or you can go back and do it the wrong way.
We can do it either here or go all the way back. So what does that mean?
I mean, like you could go and you could make an XC matrix if I get.
Oh, okay. Right. So you could do that. But in this case, let's say I set all the betas equal to 0. The model that I get is this. So when I fit, what do I get? Intercept only model. Yeah, so the coefficient beta 0 will be the average of y's. And so the residual will be the residual vector, let's say. How do you calculate the residual? Okay, so E would be like y minus as a vector beta hat 0, 1, or like y minus y bar 1. So if you want coordinate wise, it would be EI is yi minus y bar. So y bar is a constant. This one is a vector. This is a vector. So basically what you're doing is like y1 up to yn minus y bar times 1, 1. So it's effectively subtracting y bar from all of yi. So this is like empirical centering. So it's like, if you remember, we center in a random variable by removing the expectation. There you're centering these values by removing the empirical average. It's a form of centering, but in the empirical domain. So the residual for the reduced model is rather simple. And then you form the SSE, which is the sum of the squares of these residuals. And so that would give you this quantity, which is also often known as what? Yi minus y bar squared. summation. It's known as the SST. Sum squared, the total sum squared, total. So SSE for this particular reduced model is what other people call SST. And so the Ftest would be SST minus the SSE of the full model, which has another name, which is called SSR. So SSR is, so if you remember the difference between the SSEs of the reduced model and the full model, we call this extra sum of squares or additional sum of squares. That particular quantity has a different name here, like an additional name, which is called SSR, sum of squares of regression or regression sum of squares. And in any case, these are just names for this particular problem. So SSR divided by P is the number of constraints that we have. So constraints are beta 1 is equal to 0, beta 2 is equal to 0, all the way to beta P is equal to 0. Right? And so we have P constraints divided by P, and then divided by SSE divided by the degrees of freedom of the SSE of the full model, which is SSE of the full model is the degree is like the number of samples minus the number of parameters of the full model, which I call D, which has to be like most often P plus 1. So this under null has an F distribution with P and N minus D degrees of freedom. And at some point we talked about the degrees of freedom where these come from. But for now, that's what it is. You put it in a table if you want, or if you don't want, you just compute the F statistic. And there are many different formats or formulas for these SSRs and SSE, so you know already one way of doing it. So there are a lot of these orthogonality relations. So if you understand the geometry, then you can manipulate. For example, this quantity, SSR, you can write it like that. This is one of the things that you have seen in the homework problem. Sometimes if I give you X transpose X, that's enough to calculate this like fitted value. So this is like X beta hat squared. So if you expand it, it looks like that. You don't need the entire X. X transpose X is enough. And so on. So nothing especially new, except that once you do it a couple of times, you get more comfortable. Any questions? Yes.
So what exactly does that table mean? Like, so if you're doing the full model, you get the SSR, and that's how you calculate it, and then that's
it just summarizes the information that goes into this. It's like a traditional way of summarizing it. You don't have to, right? But you have like this is like it's like an analysis of variance, so decomposing the variation. So the source of variation that either coming from the or picked up by the model, the part that's not picked up is the residual, the total is here. So the degrees of freedom should add up. So sum of squares should add up. So SSR plus SSE is SST. Degrees of freedom of this plus degrees of freedom of this would be degrees of freedom. We didn't talk about the degrees of freedom of this, but the degrees of freedom add up as well. So, and then you divide this by the degrees of freedom, you get the MSR. You divide this by the degrees of freedom, you get MSE, and then you divide them. Someone wrote it like this, and people are like using it or like to use it. It's just a summary of these quantities. You don't have to work with it as long as you're understanding what you're doing. You can just write this down in one go. But you see in R some of the commands produce something like that. So you can do it for the general Ftest. So you could have between the two models. So this would be like basically this is the difference between the reduced and full model. This is the residual of the full model. This would be this is the residual of the full model here. This would be the residual of the reduced model. So this is like SSE of M reduced minus SSE of M full. This is SSEF. M reduced. This is SSEF M. And so they add up. So this is the additional sum of squares. This is the SSEF, the bigger model, which is smaller. And if you add them up, you get the SSEF that reduced model, which in this case is the SSE. So it's just a way of writing things. I'm not particularly a fan, so I'm not going to spend too much time on this. Okay. Any other questions? So this particular setting leads to another interesting quantity, which you already most likely know. It's called the R squared, or coefficient of determination. So we have this identity SST is equal to let's say R plus SSE. This is really a Pythagorean theorem, if you remember. These are basically, these two are sum of squares of residuals of two models. And if you go back to the geometry, this is just a Pythagorean theorem. So they add up to this. So if we divide both sides by SST, I get 1 is equal to SSR divided by SST plus SSE divided by SST. So this is like a normalized version. So this part, so everything is non-negative. So this quantity is going to be non-negative, bigger than or equal to 0, and it has to be less than or equal to 0. Because the other term here is non-negative. Okay, so you have two terms that are non-negative and they add up to 1. Both have to be less than or equal to 1 and greater than or equal to 0. So this quantity SSR divided by SST is called R squared. And you can see it's also 1 minus this other quantity. Okay, so if SSR is large or SSE is small, this R squared is large. So what is the ideal setting in regression? R squared should be, sorry, 1. 1 is good because if it's 1, it means that SSR is equal to SST and SSE is 0. Okay, I just want to this. SSE means 0 means that what it means. So what does it mean to have 0 SSE?
There's no unexplained variation applied.
Yes, there's no. So the residuals are all basically SSE is the sum of the residual squares. If SSE is 0, all the residuals have to be 0. Okay, so ideal. So ideal. I'm going to put in like a question mark. We'll debate about what is ideal or not. Ideal in like outcome, let's say, is to have R squared equal to 1, which is equivalent to have SSE equal 0. This implies or is equivalent to summation EI squared I from 1 to n. This is for the full model, like this is 0. And if this is 0, a little bit of math argument shows that all the residuals have to be 0. So EI is 0 for all I. Because all the terms are non-negative, if the sum of a bunch of non-negative terms is 0, every term has to be 0. And square if something is 0 is equivalent to itself being 0. So all the residuals are 0. So one thing that you can say is there is no unexplained variation if you want, okay? Explained variation. Like intuitively, what happens when you plot? Let's say if you have just a single covariate, let's say. So what would happen? Let's do xi1. What does it mean to have? So I'm gonna fit So suppose I have something like that. Okay, I'm going to write it like this. So I'm going to fit, I get estimated beta hat 0, beta hat 1. So I regress y as a regress y afterwards I1, and I get these coefficients. Okay, so I can plot this line. This is beta hat 0 plus beta hat 1, let's say x. That's my regression line or regression function. So where would the points be?
On the line.
Sorry?
On the line.
On the line. So when you fit it, so this would be like x maybe, I don't know, 5, 1, this would be x 11, 1, x whatever, x 3, 1. So these are all like different samples, and the y should be on this. So basically all the data points are going to be on this line. So then you get a perfect fit. The line passes through everything. Why? Because the residuals are 0. Okay, so that's the only way you can get r squared of 1, that all of them lie on a single line. Or all of them lie on the regression function. So when you fit the regression model, if this happens, basically there is no noise, or maybe there is noise, but you fit it to noise as well. So there is like residuals are 0. There might be noise, but you have fitted to noise as well. So in this case, it might not seem so bad. So if you really have a single line that you're trying to fit and everything is on the line, usually you're very happy. So, but it's more subtle. So r squared is equal to 1 is not necessarily good. The opposite is when r squared is 0. R squared is 0, there is nothing, it's very unlikely. Our SSR is 0. SSE is equal to SSD. So all the variation is unexplained. So there's nothing that the model picked up. So this tells you something about, some people say, strength of the linear regression model. It's r squared is sort of equivalent to the Ftest. So if you write the Ftest in our case, you can actually rewrite this expression in terms of the r squared. Okay, so as an exercise, it's going to be very good for exams as well to test. So write this in terms of r squared. So if I give you r squared and the number of variables, you should be able to calculate this F statistic in this case. So sort of there is an equivalent relation. So we're just looking at this number, it's something between 0 and 1, you can sort of get a sense of how well you're doing. The Ftest has a little bit more nonce because it takes into account the sample size as well as the number of parameters. So this is maybe a proper way, but this is just a single number, helps very quickly to get. So r squared 0.9 is really good. R squared very close to 0 is not good. It is like a multivariate kind of correlation coefficient. So in this simple regression, there's a lot of things that you can do with R squared. So in this simple regression, it is very related to the correlation coefficient, empirical correlation coefficient between yi and the xi. Okay, so we have talked about like covariance. You know about correlation coefficient, hopefully, like covariance divided by the root of the variances. So for two variables, you have the correlation coefficient. So in this simple example, if you write down the r squared, it would be equivalent sort of to the empirical correlation coefficient. For a general model, you have multiple covariates. It's like a multivariate version of the correlation coefficient. So how much y correlates with, linearly correlates with all the covariates. Okay, so it's like an extension of, so that's why they write it as r squared, because like r is a sort of mnemonic for correlation coefficient as well. Okay. R squared measures strength of the linear relation. R squared is like a multivariate extension of, let's say, Pearson correlation or Pearson correlation coefficient between two variables. Here it would be between one variable and a bunch of other variables. So y and a bunch of x's. There is a lot more to it. So it doesn't measure R squared is different from the effect size. So this is another like jargon, like term that you see like people use in applied statistics. What is the effect size? Anyone has heard that? So usually they refer to the values of the beta hats that you estimate, or the actual betas. Basically, these are the estimates of the effects. So the actual value of beta is the effect size. Okay, so potentially people think usually if you don't have enough like a statistical training, when you fit a regression model and you see a big beta hat, you say, oh, there is a significant relation maybe. But if hopefully in this course, once you like understand everything, you realize that if I observe a big beta, so I could observe a big beta hat here, like a big effect size, but it might not mean that things are significant. I might observe something which is 0.01, and it might be like significant. It might be like a very big effect in a sense. So anyone remembers this topic that we talked about? So what am I talking about? So why, for example, this could be not necessarily. So I could have like a beta hat, which is like 1,000. And statistically, it might not be significant or meaningful. Yes.
Depends on like the error or the variability of that data had depending on the sample you choose.
Right.
If you
So
were to take the sample.
yeah, so it's better to say it's related to the noise actually. So there might be noise in the model, right? So this it has a variability. Yeah. So let's like walk through the points that you mentioned. So if I resample from this model, I might observe other values. Okay. And the other values, I could be like more of like, I could observe like 1,001, next time like 999, next time like 995. Okay. In that case, what do you think?
That is probably pretty good.
It's pretty good. Yeah, okay. So yeah, so from the variation in this, you see like the variance of beta. And so the variance of beta compared to the value that, like the point estimate is what telling you the significant statistical sort of meaning. So if this situation is like this, so maybe the actual beta 1 is large, and so the variation tells you that the noise compared to the actual value is not much, maybe plus minus 5. But if you run the experiment many times, one time you get this, next time you get minus 1,000, next time you get 5, next time you get 20, negative 20, something like that. So it's all over the place, positive, negative. Then your guess is that this variation is maybe completely due to noise. So the variance of beta is 0. Maybe the center is 0, and I'm just observing large values because of the noise. So if beta 1 is 0, and the noise is very high, I can still see a lot of variation. Okay, so something could be big because the mean is big, or because the variance is big. The mean could be 0, the variance is big. So that's the part of it. So effect size does not necessarily tell you the whole story. Okay, So things could be big because the noise is large, and so that noise, the noise in the model, remember that error term, epsilon I. That could have a large variance. Sigma is big, then the variance of beta would be big. Beta hat would be big, even though beta 1 could be 0. So the mean could be 0, but the variance could. So this R squared is good because it doesn't care about the effect size, it cares about the actual sort of significance, if you want. So without a very small beta, so the situation could be like this. So if I have, so the relation between y and x could be like, the effect would be very small. So the linear, the effect being small means like the actual beta 1, the slope would be very small, let's say. Okay, I could have something like this. And if I'm very close to this line, the points are very close to this line, the R squared is going to be high. Okay, R squared large. But I could have like a case where I have very big slope. So it's like R squared large. R squared is large. Effect size small. Here it's like effect size is large. Here, the effect size is basically the slope of this line. Right? So effect size is large, but points could be all over the place around this, like something like that. So they still follow this regression line, but the noise is very high. So here R squared will be small. Okay, because you can see the residuals are going to be large. So the points are not exactly on the line. They still probably follow this, but the noise in the model is too large. So the linear relation is not that strong. It's like, or the strength is dependent on both like the level of noise and how well this model fit. So although the effects, so when you fit the regression, the beta would be large, but the R squared is going to be small. Okay, so how tightly you are around that line is what determines the R squared, which is what you care about. How well this fits the data. This doesn't fit the data very well. Sounds good. So there is a little bit of nuance that hopefully you try to understand. And any questions? It goes back, yeah.
So effect size like the slope of the line.
Sorry?
So effect size the slope of the line.
In this case, yes, effect size would be basically the value of this, which is in this case the, yeah. In general, like all the betas are effects, so, or effect, the size of the betas are called effects. So usually, at least you have to compare this to standard error estimate to get a sense. So some people, if you read like scientific literature, some people report p-values, some people report these effect sizes and the standard errors, some people report the confidence intervals. Somehow they think the effect size is meaningful. So if you have an understanding of what the size of beta should be, it might be meaningful to you. But one of the things, for example, that changes the effect size is if I rescale the covariance. So if I rescale this, all the features, the first feature, this is like one feature or one covariance, I rescale it by 10, the effective scale of beta would change. So I can multiply this by 10. So if I fit, so instead of this, I'm going to regress this on 10. Okay, let's say do xi1 divided by 10. So just rescale, like divide everything in that column by 10. What would happen if I now fit the regression? What do you guys think? It's a hard question, but what is your guess? So I fitted like a regression model LM command in R, fit yi to xi. So I just have one response vector. My design matrix just has one covariate. You can think of it as just the design has two columns of all ones and one covariate. Okay. Now I just keep this part, like the column all ones as is, I rescale the columns of the covariant by dividing by 10. Yeah,
I think beta were also divided by 10, but then R squared and status.
so which beta?
Oh,
Oh, both of them?
no, beta 0 would be the same beta 1 scale vector.
It's like divided by. Okay, any other guess?
10 times.
2 times?
10 times.
10 times. Okay, another guess is 10 times. So which one should we go? Both? 10 times this or divided by 10? I would go with this. Because this would give you, like, these would cancel out. So if you divide by this, basically you obliterate this term. Okay, so if you want to prove it, can we prove what happens, let's say? Can you, like, mathematically argue what would happen if I do this? So how do we, like, try to prove? Suppose I have, so the model is like beta 0, 1 plus beta 1, I'm going to write it as x1. These are the vector form. Vector rescaling. What happens if I now calculate this? It would be like x transpose x inverse x transpose. So let's forget about beta because I'm not going to. You can do it in general, but let's do a very simple case. Think about the simplest case. Beta 1 x1 plus epsilon. There's no intercept. Okay, so I would have like beta hat 1 is equal to what? The regression formula for this. X transpose X inverse X, right? So it would be X1 transpose X1 inverse X1 transpose Y. So what is X1 transpose X inverse? It's just the number. Okay, it's the L2 norm of X1. And so that's that. So now I'm gonna try to like consider regressing Y onto so I'm going to write it, if you have this model, I'll write it like this. So that's the underlying model, but what the regression would be like Y regress on X1. So that leads to this. So now I regress Y onto, let's say, alpha X1, where alpha is a constant. Okay. So I imagine my model is Yi is, let's call this gamma times alpha X1 plus epsilon. So alpha is a number that I'm going to pick, but then the coefficient should be different. You can also already see what that coefficient should be, but let's try to do the OLS. I'm going to like regress Y onto alpha X1. My new estimate, which I'm going to call gamma hat, what would it be, the OLS estimate? Just call this like X1 tilde. Just a new regression. The formula. X1 tilde transpose X1 tilde inverse X1 tilde transpose Y. It's just the same regression, but with a different X. Like OLS formula. So what would happen now? I plug in, right? What would I get?
It's like alpha divided by alpha squared.
So I get two, like alpha squared here, X1 transpose X1, because one alpha comes from this, one alpha comes from that. Inverse, and then X1 transpose Y. So what happens then?
So it will be alpha divided by alpha squared.
Alpha 2 comes out, right? I get 1 over alpha squared. It's a scalar. So what do I get?
1 over alpha times beta.
Times x1 transpose x1 inverse x1 transpose y, which is 1 over alpha beta hat 1. So the effect is that rescaled down beta hat. So intuitively, it should be sort of obvious if you write the model, because if this model is true, if I rewrite it like this, gamma alpha should be equal to beta 1. So gamma should be beta 1 divided by alpha. Okay. Gamma alpha equal to beta 1. So again, the true gamma should be like beta 1 over alpha if the model is correct. And the estimate will respect that. So gamma hat turns out to be 1 over alpha times beta hat 1. Okay, so do the calculation for yourself, but if I divide by 10 one of the covariates, the effect on beta hat is that I get the same beta hat multiplied by 10. Okay, so I can change the effect size arbitrarily by changing the covariance. So that's why statisticians don't care much about the effect size. It's not meaningful. It's like the product of beta and x matters. Okay, so the product of beta and x is what explains why. So the product here is the same as the previous things. So that's what matters. The effect size alone, this is another way of saying why the effect size doesn't itself explain anything. Okay, so arbitrarily you can rescale it. So if you do this, you scale the beta hat by 10, but you also scale the standard error by 10. So the t statistic is going to be invariant. So the tools that statistician use are going to be remaining like invariant. So you can't change the p-value, and you also can't change the r squared. So the r squared of the model doesn't change. If you do the Ftest is not going to change. The t-test is not going to change. But this effect size changes. Because the standard error is scaled by do the calculation for yourself. The standard error is going to be exactly multiplied by 10 as well. And so the standard like s squared, is it going to be by 10, or I'll let you figure out if it's by 10 or by something else. But you shouldn't be able to like change the statistics of the model by rescaling. Your model is not going to become easier or harder. Okay, intuitively you should be clear. I shouldn't be able to like make the model, like make the relation stronger if I rescale my covariance. So there is like this underlying tension that's there that I can't like fix. So let this be a lesson that rescaling is interesting. So as a statistician, you're a statistician, you can rescale things, and if things vary, change, or something happens, then you have to be worried a little bit. Your conclusion sort of, let's say, shouldn't be changing if someone rescales the covariates, let's say. In any case, rescaling or scaling up and down is something that you can use. Okay, and you have tools to figure out what happens to all the quantities. So what happens to the standard error, what happens to the actual beta hat, you know, all these things you can calculate. What happens to the variance of beta, so good questions? Yes.
So when you do the transformation on xi, maybe, so if the data is not good enough, so you do the transformation on xi, so is that going to change the r square or the beta hat?
That is what I mentioned. So if I do this transformation, let's say,
It's will change.
what will change?
The effect size will change.
The effect size will change. We just saw it. Does r squared change? Anyone knows whether it's going to change? No. Can you prove it? How can you prove that it's not going to change? So if that's the case, you just showed that if you rescale x1 by 10, you divide by 10, you multiply beta hat by 10. So fitted value, what happens to the fitted values? Fitted values don't change, the residuals don't change. Residual sum of squares don't change, so SSE doesn't change. SST doesn't depend on this part, just depends on y. So SST doesn't change, so R squared doesn't change. Okay. So this procedure cannot change the R squared. So R squared is robust to rescaling the polarity. So this is another conclusion we can add. So 1, 2, 3, 4. R squared is invariant to rescaling the covariance. Effect sizes are not. The F statistic is also like that. It's easy to see, like if a statistic is also based on SSR and SSE, so you can also actually write it as in terms of the R squared. So if a statistic is not going to change as well. So the p-values are not going to change. None of the statistical conclusions are going to change by this procedure, although the beta hats are going to change. The standard errors are going to change. But the t-test, f-test, and R squared, these are going to remain invariant. Sounds good? What else? Any questions? What else do you know about R squared? Is it good to have R squared of 1? Good, bad? R squared 0, probably not good. R squared 1 looks okay, but is it really good? This is this question mark here. Is it ideal to have R squared of 1? Yeah.
It depends on the x's. X. Like if it's multiple, you might like correlate to each other.
Okay, so if you have one x, okay. If you have multiple x's, they could be correlated, okay? But what is wrong with being correlated? So actually, if they're correlated, it's not going to increase R squared as much. That's an interesting observation in the opposite direction. So if I add, if I have one covariate, and if I add one more covariate is very correlated, this is not going to explain much beyond the first one. So I can't increase the R squared that much. So if you add a bunch of correlated, so if you want to see like intuitively from the geometric picture, what would happen is, so you have this image of X, right? So this explains, if you recall this image, it's just this picture is going to help a lot. So you project Y onto the image, you get mu hat. This is E. Basically, the ratio of the size of this to this is what determines the R squared. Or basically, okay, this part sort of almost like if Y bar was 0, the size of this divided by the size of mu hat divided by the norm of Y hat. Not Y hat. So the norm of mu hat squared divided by norm of Y. So the norm of Y squared is very close to SST. So if Y bar was 0, let's say I remove the mean of Y. So the Y's empirically have 0 mean, then the norm of Y squared is SST. The norm of mu hat squared is the SSR. The SSR divided. So this is if the situation is like this. This is very close to this image. Mu hat is like the size would be close to the size of Y, so R squared would be large. R squared large, R squared is smaller. Okay, so in the ideal case, Y is entirely in the image. In that case, R squared would be 1. So SSE would be 0. So geometrically, it measures how close Y is to the image of X. Okay, and now if I add more covariates, I'd increase the size of image of X. Right, so image of X would become bigger. But if they're correlated, it's not going to get as big. So I would, so actually, that's not correct. Let's see. Because that, okay. It's actually a very good point. So if I add something which is exactly correlated, just like a scale multiple, I'm not going to change the image. So I'm not going to change the R squared. But if I have something which is highly correlated with X, but not exactly correlated, did what I mentioned was correct or not? So can I increase R squared? It's actually tricky because every time I add one X that is not perfectly correlated with the other X, it's outside the image. So what happens is that I can project that X onto the image and there's an orthogonal component. So the space, the span of the new image would be the previous image direct sum with the orthogonal complement of that. So whatever new direction that the new X brings. So that would add one more dimension. If I add one more dimension, I can potentially explain more of why. So that I take that back. It's like it's a little bit more complicated, but it's a very good exercise. I should probably write a homework problem so that you can figure out what happens if you add correlated variables. Intuitively, you shouldn't be able to explain why better, but now I'm a little bit. They probably can come up with cases where, because you still have a bit of component and you can put a lot of weight on that component could potentially explain why. But if you do that, the issue is that if you give me like a completely orthogonal component to everything else, that would be good. I can increase R squared. But if you give me a new covariate which has like a component which is the large component which is already explained by the rest of the x's, it's in the image, and a tiny component which is outside orthogonal to the image, I can use that tiny component to explain part of y, but then I have to rescale this entire covariate. So I also like increase the, I have to indirectly use that component because it's part of the new x. So if I put a lot of weight on the new x, I also put a lot of weight on the part that's already in the image. So actually, this is a very good example of what happens, which I want to talk about next, which is multicollinearity. What happens is, if you do this, and if that extra component explains why, you entirely change the coefficients of the original ones, because it's a little bit hard to explain. But it's a very good point. We'll come back to it, and I should probably assign as a homework problem. So this goes back to the idea of multicollinearity. Okay, so you can, as long as you bring in new directions, things that are orthogonal to the image, you can potentially explain more of why. But in that case, I think probably R squared can go up. But what happens is that you like entirely affect all the other betas, and we'll see what happens, because you want to like incorporate that coefficient that would also alter the component of that new x which is in the image, and because that changes, all the other things in the image have to readjust to like cancel out the part that you're now adding. So it's a very interesting problem, but let's like put that aside for now. So what happens if you increase, like add correlated variables? So the interesting thing would be add uncorrelated variables. So I can add uncorrelated variables and potentially increase R squared. So you keep adding more uncorrelated variables, and at some point you can reach this. Okay, so if I keep adding covariates such that the dimension of the image, so y is in Rn. If the dimension of the image becomes n, it spans the entire space. Okay, so one vector, the image of one vector is just one dimensional. The image of two linearly independent vectors is two-dimensional. 3 would be three-dimensional. for 4-dimensional up until n vectors would be n-dimensional. Because I usually have one vector of all ones. So if I add n minus 1 extra covariates, so if P, so we have 4, 5, we can always, this isn't, again, tentative, make r squared equal to 1 by adding, let's say, linearly independent covariates until we are at P equal n minus 1. So if I have n minus 1 covariates in the model, and I have one covariate of all ones, I get n linearly independent covariates. Okay, so I have like 1, x1, x2, all the way to xn. And this matrix is then, it's going to be n by, so this n minus 1, sorry. This would be n by n. And if it's full rank, that design makes n by n. If it's full rank, then I can perfectly explain why. Okay, y would be that the residual will be 0. And this is easy to see because my beta hat would be like x transpose x inverse x transpose y. Let's say this is full rank. Because x is n by n. Okay, and then because it's full rank, it's invertible. So what happens is that this I can actually break down. In general, you can't break this down because these are rectangular matrices. But at this point, when I hit this, I can just break it down. I get inverses are like transpose. So I get the second one inverse times x transpose inverse times x transpose y. And these would cancel out. Right, so this would be identity. So beta hat would be like x inverse y. So what would be the fitted values? Yeah, x beta hat, which would be like x inverse y. And so you can see like fitted value would be equal to y. So residual would be 0, r squared would be 1. Okay, so you can perfectly, and this is like algebraic way of saying it. Geometric is that the span on this is going to be Rn. And you project y onto Rn, it's going to be itself. So in your head, it's going to be itself. So I can always do this. So this is not necessarily good. Why it's not necessarily good? Anyone knows why? Keep adding covariates until you hit r squared 1 is not necessarily ideal. Yeah.
Some of the covariates might not be important, or like they might be unimportant, and they appear to be important, but things are squared equal to 1.
Okay, but it doesn't fully like get the why they're not important. They're trying to explain why. So I'm perfectly explaining why. Why do you think they're not important? I managed to explain all the variation y away. Okay. Is there anything wrong? This is not an easy question to answer in light of deep learning and ChatGPT and stuff, but there is a relation to ChatGPT here. There is a reason why you don't want to do that in a statistic if you believe there is noise. Okay, so if you believe y is noisy, if you do this, you're also fitting to the noise. Okay, so you're explaining noise as well. But that's not what you want to explain. Your goal is not to explain the noise part. So if you believe that there is this part in the model, at this point you've explained the entire variation in y, including the noise. So you've made your model complicated enough to be able to actually predict the noise as well. But you don't want to do that part. You want to explain this part, which could be done by a much simpler model if you can. And so to try to explain all the variation in y, you're going to explain all the variation, including the noise, and that part makes your model complicated. So this model might be very complicated. And later on, because if you resample from this model, the noise is going to change. This part is not going to change. So the data are not going to change, hopefully. but the noise is going to change. So because you have fit to this particular noise, the future noise is going to be different. The noise is not the structure. So you're going to pay a big penalty usually. Okay, so if you have noise, what would happen is something like, there's a name for this. Anyone knows the name? What is this phenomena that you're like dealing with? Overfitting, yeah. So we have overfitting or fitting basically to noise. So suppose, for example, that my data was actually like perturbation along the line. So there was this really nice linear regression model. Okay, so let's do simple. Yeah, so I have a bunch of points here, especially if you have few points. And then maybe later on, if you add more, get more samples, they're going to be around this line, just randomly scattered. What happens is that I can, for example, so the actual model is like yi is equal to beta 0 plus beta 1 xi 1. A simple example in this case to add additional covariates. How can I add additional like linearly independent covariates? What do you guys think? Just have one covariate. How can I like create more? I think I talked about this earlier, like polynomial regression. So this is like the true model, let's say. But I'm going to fit a model that looks like this: beta 0 plus beta 1 xi1 plus beta 2 xi1 squared. So I square the covariates added as a new covariate. And then beta 3 xi1 3, just a single covariate, and like keep adding it, like up to beta p xi1 to the p plus epsilon I. So what happens is that as I increase p, I can just keep adding these. And I can hit n. It's polynomial of degree n. Actually, in this case, degree n minus 1 is good enough. So if you have a polynomial of degree n minus 1, it has n coefficients. And then usually you hit, if the covariates are variable enough, you hit that barrier, you get R squared. So what happens if I fit something like that? Let's say p is equal to n minus 1 and everything works out. I end up perfectly fitting. So I'm going to pass a polynomial through this, and it would look like this. So it just, this is called interpolation. So when you fit through everything, so all the data points are going to be on this. Right. So if this was all that there is, it's okay. But later on, so this is called interpolation. Interpolation is like you pass a curve through all the points. The points are all on that. So residuals would be 0, fitted values would be exactly equal to yi. So you're going to be, so this is going to be a linear function in these covariates, but when I'm going to plot it as just a function of, because there's just one x here. If I plot it as a function of x, it would be like a nonlinear function. Okay, so polynomial regression, you can think of it as a linear model in these extra covariates, or as a nonlinear model in the original covariate. So this is that viewpoint. So you plot it, it's just in the polynomial xi1, yi, and so that's what happens. So this is not good if you have noise, because later, if I add more data, they're not going to come from this polynomial, they're going to come from this line plus some noise. So new data points are going to be maybe here or here or here or here around the line. Okay, and generally it might be that the line, if you fitted the line would have a better predictive power than this guy, because the issue is this is still okay. When you fit polynomials, it could be like a polynomial, and you try to fit it, it could be like this, and it just goes down here up there to pass through these. So if that's something like this happens, this is still a perfect fit. It could happen, but it's going to be bad for future data points, because the future data points are going to be close to the line. This part, which you haven't seen any data yet, this had to like twist itself to pass through these points. And so this is going to be very bad. So these effects that are produced. So this polynomial fit that I had, if you could get something like that, it would be okay. So predicted, not necessarily the best prediction, but this could also happen. And then for future data points, this is far from any of the future data points that you're going to see. Because most of them are going to be line with line. Their predictions here would be very bad, and there would be very bad. So generally, when you do this, you decrease predictive power. Like in machine learning, they call it generalization error. So how to generalize future data points that's effective. From a statistical perspective, you're doing something which is more complicated than necessary. So ignoring this blue one, even if you have the purple one, which is sort of close to the line, it's more complicated than necessary. So traditionally, people prefer the simple models. So if you can explain everything by just a simple model, it's much more easy to interpret than if you have like many, like how do I have to interpret the fifth power here, for example, and the sixth power, and so all these variations have to take into account. If you can explain it by just a simple model, a simple linear model, or like quadratic model, that's traditionally preferred. It's called Occam's razors. If you can explain by a simple model, you should go with a simple model. This is like a philosophical issue. You can debate with people whether complexity is good or bad, but it's like another consideration. But the main issue is this overfitting could potentially hurt you in predicting future data points, because you're, especially with polynomials, this could happen. The polynomials could behave very erratically, yes.
So you get the overfitting phenomenon even if you do with the polynomial, if you do a nonlinear regression.
So if you do polynomial, this could happen depending on how the data points are set up. The purple one could happen, or this could happen, especially at the boundaries where you don't observe. So for example, the linear regression, so the prediction outside the range of X is reasonable. It's like linear interpolation. But for polynomials, when you go outside, they could like behave very erratically. So the prediction here is going to be really off most often.
But it's still overfitted. We would say that the R squared would be equal to 1, or that R squared.
Overfitting usually is usually stated when you reach this level of interpolation, right? So close to this, or like interpolation, people call it overfitting. Whether you're actually overfitting or not is a different story. Overfitting is fitting a model which is more complicated than it actually is. Okay, so you're fitting something which is, so if the actual model is really a polynomial of degree n-1, then you're not overfitting really. But let's say if the actual model is this, and I'm fitting a polynomial of degree 20, or let's say I have 50 samples with polynomial of degree 49 to this, then I'm overfitting because I'm fitting a much more complicated model.
And
So overfitting
R
is,
squared a thing for non-linear models, or is it just,
so
is that reserved for linear?
what is your guys' answer? Is R squared reserved for nonlinear models? Are we doing anything nonlinear here? So this is a nonlinear relation between y and xi, but I can treat it as a linear multiple regression if you think of these as new covariates. So that's what I'm doing. So you can think of this as xi tilde 1, xi tilde 2. This is a new covariate.
Square everything in cubic, square that in cubic before you run the regression. Then
That's what we do, yeah. So if you want to do this, you can like basically create a design matrix, which is like 1 here, xi1 here, xi1 squared. So these are just the square of every element here, so 0.1 squared, and then all the way. So you get a new design matrix. Now you fit this linear regression. So you just create covariates, new covariates from the original. So this is really a linear model in this sense. So there's meaning for R squared. So you see, like the linear regression is not that restrictive. Well, that's what happens. So what should we do then? So if R squared is not in itself Good enough. So this would come up in one of the things that would come up is in a P, because this is going to go close to 0, and so the F statistic will pick up. So the statistic would be affected. So the F statistic is sort of interesting. It's not only R squared because it takes into account the degree of freedom. So that's sort of okay. There are other things that we can do with. So if a statistic is more robust, let's say, can tell you something still, but it's still a little bit debatable. We will talk about what happens. Like you can modify this to something called adjusted R squared. That's a better. So the idea of where to stop here, at what degree, let's say, if I want to put a polynomial regression, where should I start? Let's start like at this point or at this point, the second degree is third degree. That's called the problem of model selection. So how many of these covariates I need to include in the model? In general, if you have a regression model, I want a subset of the covariates smallest that explains the y the best. And if you want to go for simplicity, where should you stop? R squared itself is not helpful because R squared is going to be increasing. As I add more covariates, it's just going to improve. So we need other measures. You can do it at the Ftest, but there's variations of this, which we talked about when we talked about model selection. So this is the idea of model selection. Model selection is a little more complicated. So you have to balance the complexity of the model relative to the fit. So R squared is a measure of how well it fits the current data, but usually you need a measure of complexity of the model or the performance of future data, something else which is in tension with this. So usually you balance the two out, and that will give you the idea to select the right model. Okay, so we talked about a lot about this. Next time, there is this comparisons of treatment. This is another like a special case of the Ftest. I might go very quickly over it or ask Jan to probably go over it in the discussion on Monday. So go to the discussion. There's nothing special. It's just that this is another case where you sort of seen, you also see in your problem, you have multiple groups, and you're gonna test whether the response of each group is the same or not. And you can formalize it as a regression model and then test whether the group effects are the same. That's another example of the Ftest. Once we're done with that, we come back to a couple of other things like quadratic form, Gauss Markov theorem, and then move on. Okay. Thank you very much.